This is problem session 20. And the last lesson was on concavity. And the lesson today is on limits at infinity. Are there any problems you would like me to do? So concavity is lesson 19, chapter 4, section 4. Maybe I'll do one or two problems and see what the response is. So for example, in section 4.4, number 27. You have the function f of x equals x times the square root of x plus 3. This is defined for all x greater than or equal to -3. And the first derivative is the square root of x plus 3 plus x times the derivative of the square root of x plus 3. That's 1/2 x plus 3 to the minus a half. So this is the square root of x plus 3 plus x over 2 times the square root of x plus 3. And if I put that over a common denominator of 2 times the square root of x plus 3, I get 2 times x plus 3 plus x, which is 3x plus 6 over 2 times the square root of x plus 3. If we want to find the inflection points in the concavity regions, we need the second derivative. So the second derivative, it's the quotient rule. So we square the denominator. That's 4 times x plus 3. It's the derivative of the numerator, which is 3 times the denominator minus the numerator times the derivative of the denominator. The derivative of the denominator is 2 over the square root of x plus 3. Over 2. So just the 1 over the square root of x plus 3. So what we have is then these 2's cancel. So I get 4 x plus 3 to the 3/2 in the denominator. I have 6 times x plus 3 minus 3x plus 6. So 6x minus 3x is 3x. 18 minus 6 is 12 over 4 times x plus 3 to the 3/2. This is always positive. So the second derivative is 3 times x plus 4 over 4 times x plus 3 to the 3/2. Maybe I'll check that this is correct. So f of x is x times the square root of x plus 3, x greater than or equal to -3. First derivative is x plus 3 plus x times 1 over 2 times the square root of x plus 3. So that's 2 times x plus 3 plus x. That's 3x plus 6 over this. I could, if I wanted, write this 3/2 times x plus 2 over the square root of x plus 3. And when I differentiate this by the product rule, I get an x plus 3 in the denominator. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. So that's 6x plus 3 minus 3x plus 6. That's 3x plus 12. Yeah. So this is greater than 0 for all x greater than -3. So this is concave up everywhere, and there are no inflection points. There is no inflection point. That's all it is. Let's look at one more. Try number 23 in the same section. So f of x, this is a 4th degree polynomial, 1/4 x to the 4th minus 2x squared. A 4th degree polynomial typically looks like this, and this is degenerate in some way. First derivative is x cubed minus 4x, which is x times x squared minus 4, or x times x minus 2 times x plus 2. So this curve is going to have a relative maximum and a relative minimum. It's going to have its critical numbers at 0 plus or minus 2. What's the second derivative? It's 3x squared minus 4. So that's 3 times x minus 4/3. So this equals 0 when x is plus or minus the square root of 4/3, which is plus or minus 2 over √3, if you like. It's a perfectly good number, a little bit bigger than 1. So this is going to have 2 inflection points. And f of x is concave up when second derivative, x squared minus 4/3, is positive, which means when x squared is bigger than 4/3, the absolute value of x is bigger than 2/√3. And it's concave down, and the absolute value of x is less than 2/√3. At the points where you have the derivative equal to 0, f of 0 is 0. F of either plus or minus 2 is 16/4 minus 8 is minus 4. So this curve looks like this. And here are the inflection points. Here the curve is concave up. Here the curve is concave up. And here the curve is concave down. Very pretty. No questions? I'm not sure anyone's here, but we'll go on. Section 4.5, limits at infinity. These are the horizontal asymptotes. So the idea is you might have a function whose graph looks like this. And we would say the limit as x goes to infinity of f of x is equal to L if for all epsilon greater than 0, there exists an integer, not necessarily an integer, a number m, such that f of x minus L is less than epsilon for all x greater than m. And there's an analogous definition for the limit of f of x as x goes to minus infinity. The most interesting case is for limits of rational functions. And there are three cases. So a rational function f of x is a quotient of polynomials. It might be of the form ax to the m plus lower order terms divided b sub n x to the n plus lower degree terms, where am is not 0 and an and bn is not 0. And the limit of this function as x goes to infinity, there are three cases. If m is bigger than n, this polynomial is higher degree and the limit's infinity. If m is less than n, this is of higher degree, the limit is 0. And if m equals n, if these two polynomials have the same degree, It's the ratio of their leading coefficients, AM over BN. That's really the basic fact that you have to remember from this section. Let's see, I'm really curious who's actually here. So if you would, just please go to the chat and just type in present, so I know you're actually listening and not just have a computer on. Oh, good. I have one person present. Anybody else? Two. That's not bad. That's a start. Anybody else here? Oh, let me just do a few problems. And the purpose of these little Zoom sessions is to answer questions, not so much to go over the lectures, which have already been posted on YouTube. So let me look at one or two of the homework problems. We have 17 to 25, the odd numbered problems. So this is section 4.5, number 17. So for part A, we have the limit 5 minus 2x to the 3/2 over 3x squared minus 4 as x goes to infinity. Let me just write this. So I have the highest power of x starting off each expression. This is 3x squared minus 4. This is minus 2x to the 3/2 plus 5. If I look at the exponents, 3/2, 2, the denominator has larger exponent than the numerator, so the limit is 0. In part B, I have 5 minus 2x to the 3/2 over 3x to the 3/2 minus 4. Again, let me write that with the highest power of x appearing first, minus 2x to the 3/2 plus 5 over 3x to the 3/2 minus 4. Now, the highest power of x is the same in the numerator and the denominator. So the limit is just the ratio of the leading coefficients of each term, minus 2 over 3. In part C, it's the limit as x goes to infinity of 5 minus 2x to the 3/2 over 3x minus 4. Again, I want to have the highest degree term appearing first, 3x minus 4 minus 2x to the 3/2 plus 5. Here you see 3/2 is bigger than 1. So the numerator, the highest power of x in the numerator is larger than that in the denominator. So this goes to infinity. Number 19, we have the limit as x goes to infinity, 4 plus 3 over x. 4 goes to 4, and 3 over x goes to 0. So the limit is 4. And number 21 is the limit of 2x minus 1 over 3x plus 2. The highest powers of x in numerator and denominator are the same. So the limit will be 2 over 3. In problem 25, we have the limit of x over the square root of x squared minus x. I can write this as the limit of x over the square root. Let me just factor an x squared out of this. X squared times 1 minus 1 over x. This is the limit as x goes to infinity. X over square root of x squared is x times the square root of 1 minus 1 over x. These x's cancel. This is the limit as x goes to infinity of 1 over the square root of 1 minus 1 over x. This goes to 0, so the limit is 1. So we're still sticking with section 4.5. Number 23 is the limit of x over x squared minus 1 as x goes to infinity. This has degree 1, this has degree 2. 1 is smaller than 2, so the limit is 0. Number 35. Oh, this is interesting. The limit of sine 2x over x as x goes to infinity. So the sine of 2x is always an absolute value less than 1. Its sign is always between plus 1 and minus 1. So the sine of 2x over x, in absolute value at least, is less than 1 over x. We're only looking at x positive. So this expression is less than 1 over x, and 1 over x goes to 0. So the limit of sine of 2x over x is 0 as x goes to infinity. Okay. So I just went over all of the homework problems in section 20 on limits at infinity. It's a pretty easy and short lesson, I think. I'm happy to answer any questions about this or anything we've done so far. Keep in mind that there's one more lesson before the next exam, lesson 21, which is on optimization problems, section 4.7. Next Monday, we review, and the exam is a week from Wednesday. So that's where we are. Are there any questions? I mean, I'm happy to answer questions if there are any, but if they're not, we can quit. I posted office hours 3 times coming up this week. So if you do have questions, I encourage you to log on during one of those Zoom sessions and ask me whatever questions you might have. All right, so if there's nothing else, then I guess we'll quit. Again, check Blackboard for this class, the Blackboard website, and you'll see the office hours. I think the first one is this evening at 7 p.m. because I know a lot of people work during the day and have trouble finding other times. Okay. If there are no questions, that is it. Everyone stay well. Be back on Wednesday. Same time, same place.